Welcome to the real world.
We're going to be talking about matrices today, right? Or if you prefer matrices, either one is fine with me, even though matrices is the correct word. Who's heard of a matrix before, mathematically speaking, right? If you've taken algebra, you've probably dealt with these things, right? We're going to talk about what you've probably seen and a few other things, okay? There's a lot of stuff we got to go over today, all right? Definitions and notation, math, the identity matrix, a transpose matrix, powers of matrices, symmetric matrices, binary matrix, joins, meets, and Boolean product. All that today. We're going to do it.
What is the matrix?
You guys thought I wasn't going to do it. I did it. What is the matrix? What is a matrix is what I should say there.
The matrix is the world that has been pulled over your eyes to blind you from the truth.
I forgot I put that one in there. It was late, man. If you guys don't know these references, please, for the love of all that is holy, go watch the Matrix trilogy. Every Christmas Eve, I wrap presents all night, and I watch the Matrix trilogy while I'm wrapping presents. Every single Christmas.
Most Christmas movie of all.
Totally, man. All right, so the matrix is just an array of numbers, right? This looks like a two-dimensional array in the world of programming, right? If you're familiar with those, hopefully you are. But when we use these square brackets here to notate them, but this is a matrix that contains 1, 1, 0, 2, 1, 3, right? We're going to learn more about why and all that in just a moment, but for now, let's kind of get some basic notation down, make sure we understand what's going on here. All matrices are referred to as a row by columns in their size, right? So how many rows are in this thing? And how many columns? Yeah. So 3 rows and then 2 columns, right? And I want to point that out because often people forget which way is row, which way is column. And they also, the other one people forget, and I'm included in this batch, is X and Y on your graph. It took me forever to remember which one's which. Anyway, this is a 3 by 2 matrix, okay? The dimension of this matrix, again, is 3 by 2, all right? This becomes very important when we're going to do arithmetic with a matrix, which we'll see in a few minutes. So here's just some basic notation. I used a table here just for a moment so we can kind of see how this plays out. And so you can see across the top that I've got it labeled column 1, column 2, column 3, all the way up to column N. And then I got row 1, 2, 3, all the way up to row M. Okay? The first column there, the first spot in the matrix, and remember, imagine that the curly, or not the curly braces, but the square brackets would be right here and right here, right? Around this material here, around this table. We're going to get rid of the table structure in a minute, but it's just good for doing this little part of the presentation. So the first cell right here, the top left, is referred to as, we just use A as a variable here, but it's 1, 1. That's subscripted A1, 1, as in row 1, column 1, right? A1, 2, right? Row 1, column 2, 3, and all the way up to A1N. Dig it? Okay, pretty straightforward. Then the next row would be A21, A22, A23, A2N. Yeah? Then the last row here is AM1, right? It's all the way to the mth, if that's even a word. Then row M, column 1, row M, column 2, and on down the line, okay? The last one in the grid is AMN. So that notation is important, and it's going to help us as we go forward and we do a little bit of arithmetic with these things. Of course, we will ignore in the real matrix, you don't actually show those column and row headers, and in fact, you don't have the table-looking structure, you just have big fat angle brackets, right, or square brackets, okay? So that's the basic layout, the basic notation of the matrix. If you want more details, page 127 for more notation and stuff like that, right? I've been trying to put page numbers in these PowerPoints for you guys so you can more easily look it up. So let's take a look at how to do some math. Any questions about the basic notation? It's pretty straightforward. I think we're okay there, okay? So matrix addition. Matrix addition is pretty simple. It's the multiplication that's a little tricky, all right? So matrix addition is simple. Who knows how to do this? Anybody? Yeah. What do we do?
They're the same dimension. You can just add them straight across each element with each corresponding
Yeah, exactly right. Yeah. So we got a couple of rules here of how it works, but that's exactly right. First of all, they must be the same dimensions. That's the very first thing you pointed out. They don't have to be squares, right? They can, as long if they're both a 9 by 7, then that's fine. If one's a 9 by 7, the other's a 7 by 9, nope, won't work. Okay, so they have to be the same dimensions, and these are both 3 by 3s. Then the resulting matrix is the same size as the original two matrices, right? And you add each cell in A with its corresponding cell in B, right? It's pretty straightforward. So that's, what cell is that? A11, right? We're going to add that with A11 in matrix B, and that gives us the answer 4. Fabulous. All right. So let's just go around the room here. Jace, what's this one going to be? 3. All right. Brian, that one.
2.
Nice. Josh, this one. I moved. Yeah, I moved it on you. That will be -2. Yes, very good. And if any of these answers that people are giving, you're not sure where they're coming from, please stop me, okay? Craig.
That is -3.
That is -3, yes. And then Chad, which is who I meant to say. 2. Yeah, sorry about that. I was looking right at Chad when I said that too, sorry. Very good. And then let's go with Andrew. What's the, I think I'm just gonna have all 3 of them show up, so what's the top one there, Andrew?
4.
4, JP, the middle one? -1, and Yuri, the last one?
5.
4, -1, 5. Done? I think it's pretty straightforward, it's not that complicated.
It's the question that drives us.
So, any questions? Sorry. All right, good. So, matrix multiplication, all right? Multiplication with matrix is a little bit trickier. So, a couple basic rules. Rule number 1, the number of columns in matrix A must match the number of rows in matrix B. All right, and we're going to do a nice little visual here to understand that in just a moment. It'll be the number of rows in A by the number of columns in B, right? So here's an example. Matrix A. What's the dimensions of that?
3 by 4.
Yeah, 3, how much?
4 by
4 by 3. I heard a 5 out there. I'm not sure what that was. Okay, yeah, 4 by 3. It's row by column is always how we determine them or denote them. All right, and then B, how big is B?
3 by 2.
3 by 2. Yeah, 3 by 2. All right, so that's a 4 by 3, that's a 3 by 2. Now, what we want to figure out is what is A times B, okay? And that resulting grid will be a 4 by 2 matrix. It'll be the number of rows in A by the number of columns from B. See that? So if we look at this rule here, there's a slide that breaks this down that's got all the little graphics. I'm about to put them on the screen. That it's in the condensed version for you guys to look at if you want. But this will be the resulting matrix. It'll be a 4 by 2 matrix. And this first rule here, here's what this means. Those two numbers right there, they need to be the same. If those two numbers are not the same, you cannot do the multiplication, okay? And again, the matrix is written as row by column, so 4 rows by 3 columns, and then 3 rows by 2 columns. If those two middle numbers are matching, then we're good to go, all right? The second rule here, resulting matrix will be an A number of rows by B's number of columns. That outer two numbers, that will be the actual size of the final matrix, okay? So that's a way to sort of visualize that and make sure you can see, just by looking at two matrices next to each other, you can know if they're going to work out or not. Okay? Good? Can I do B times A?
Sure, but it will be different. No.
Actually, you cannot.
Oh, not in this case.
You cannot in this particular case, right? Because that would be a 3 by 2 and a 4 by 3, and the two middle numbers would not be the same, right? The rows from one must match the column from the second one. So in this case, we could not do that. You see those little tails hanging off my little lines right here? See those? When I made the slides, they were not there. Gremlins came in overnight and did something, man. I don't know what's going on there. All right, so there's the resulting matrix right there, the 4 by 2. It's the outer two numbers, okay?
It's the question that drives us.
I remember that time. Any questions? That's the basics. Now, we're going to walk through a problem, right? There's how do we do the actual math is the next step. But this part, just I wanted to make sure you understood, how they relate to each other, right? So let's walk through the actual math of it now. This is, again, it's not super hard. What I love about the fact that I'm doing this on a PowerPoint, there's something I always tried to help the students visualize, but with a whiteboard, it's really hard to do that. With this, I can actually animate the PowerPoint so you can see it really well, okay? So the resulting matrix here is going to be, remember our notation, this will help us actually get some clarity here. That's the first one is A11, the second one is A12, and so forth down the line, right? And the first number in the subscripting there is the row, the second number is the column, okay? This can be very useful for us. So we're going to figure out what is that number first. Let's just do it one at a time. And whenever you do these math problems, the first thing you do is figure out how big is the new matrix, the final matrix, right? Draw that out and then just work on each number in the matrix. So how do we figure out this number? Does anybody know how to do these, by the way? Just show of hands, one or two, a few? Okay, good. So we'll go through it relatively quickly, but you can walk through the slides again, watch the video again, and obviously pause for questions. Now, some of you know the method, just by show of hands, there's a method where you kind of stack the matrices on top of each other and you stagger them over. Does anybody know that method for doing multiplication? Do you know that one? If you know that method, I'm not going to teach it because I don't like that method. It messes with my brain. I like this method better. But if you understand that method, feel free to use it. And if you want to ask somebody else in the room later how it works and they explain it to you. So far, though, every student that I've there's usually one student or two that knows that method, and I'll have them explain it to the class, and everybody doesn't like it. Never anybody like it. So maybe you'll convert to this new method, Chad, or you'll still stick with the old one. Either way is fine.
Doing in my head, I just know that method where you like turn B on its side.
That's what we're doing. Yeah, that's what we're gonna do. There's a different method where you don't flip the numbers or anything. You just stack them on top of each other. It's really weird. So maybe you're thinking of a different one. So here's what we're gonna do. Remember, look at the square on the right there, the A11. That A11, that first one there, is going to be coming from row 1. It's labeled row 1, right? That's what the 1 is. But it's getting those numbers from row 1 of the first matrix. And then that second subscript to number 1 is getting that's the column. It's getting those from the first column of the second matrix, right? So we're going to do math on those two sets of numbers, and that's going to ultimately give us that final square on the right. Does that make sense? I mean, I haven't shown you how to do the math, but is that conceptually, we see where they're coming from? Okay. So I try to visualize this, and let me show you one more, then I'll show you the visualization. The second one, so take a look at that square on the right, A32 or A32, that's row 3, column 2. That number will be created by looking at row 3 in the first matrix, column 2 in the second matrix, right? And it's right there in the name of the notation, okay? Make sense? So we're going to look at one here. I've just moved the numbers, the whole matrix over to the right there, and so I took off the brackets so I can do a little animation. It just makes it a little bit easier. Take a look at 104 there. That's 104 in the first matrix, okay? Imagine it rotating like that, okay? If you can imagine that rotating on its side there, okay? I'm going to move it back so you can see that again. The relative position of the numbers don't change. We're just imagining it becoming vertical, right? And then I'm just going to rotate the numbers so they look normal, right? But then what we're going to do is we're going to multiply those numbers to each other, 1 times 2, 0 times 1, 4 times 3, then add it up. That number will be A11 in the resulting matrix, okay? We're going to multiply them together, add them up, and that will go in that red square there. Because remember, what's that red square? It's row 1, column 1. Which is what is its position in the new matrix, but it's also coming from row 1 from the first matrix, column 1 from the second matrix, right? So what's the answer going to be for that? 14. Yep. All right. This one I rotated the numbers there. I didn't show the animation, but we were rotating those numbers, and we're going to do the math again. So 2 times 2 plus 1 times 1 plus 1 times 3 is 8. I heard a 10 out there, yeah. Yep. All right, the next one here, let's go, I don't think you got to play last round, Kyle. What's that going to be? Yeah, what's the result going to be?
7.
That sounds right to me, 7. All right, Sergio, what's this one? That looks right to me. Yep. All right. So I think we're getting the picture here. It's not too complicated. Now we're going to look at the next one. And remember, row 1, column 2. So it's going to come from row 1 from the first matrix, column 2 from the second matrix, right? So again, we're gonna multiply the row 1 on the left, 104, times 410, column 2 on the second matrix, right? Josh, next one.
9.
Very good. All right, JP, next one. Good. And last one, Jace.
2.
That sounds right. Yep, 2. Yay. All right, yeah, they're not too hard to do in your head with smaller numbers, and especially the type of matrices we actually care about, we'll learn about in a minute. They're really easy to do in your head, really easy, okay? So this is our final resulting matrix, and again, it's a 4x2 matrix because the original one had 4 rows and the second one had 2 columns.
It's the question that drives us.
Any questions? Let's take a look at a couple more examples here. Here's a simple matrix right here. It's a 2x2, so it's a square matrix. And we got another one called B, that's also a 2x2 square matrix. So can we multiply them? First question. The answer is yes. How do we know that? What's that?
Has the same dimension, so it still matches.
Yes. So the fact that it has the same dimensions, yes, coincidentally, that does end up panning out correctly. But the real thing we care about is rows from A match columns from B, right? So in that case, we can't. So we can figure out what A times B is, which I think we could all do this math. I don't think that'd be too hard. We just walked through it a second ago. But if you need a moment to pause and look at the video here, make sure you understand how we got those numbers there. And maybe we should double check them, make sure I didn't make any math errors. In fact, no, I know I've got the key right here. So 3, 2, 5, 3, yeah, we're good, okay. So I'll just keep this handy, prevent any typos. So the next question is, what's B times A? Can we do that?
Yeah.
Yeah, we can, because the B now being the first matrix, the number of rows in B matches the number of columns in the second matrix A, right? And that's fine. So we can do it. The real point that I want to get to is this, and make sure that the math is correct. And if you want to pause and make sure you understand how we got there again, feel free. But notice, very important lesson here, folks. A times B is not the same thing as B times A, okay? It is not the same thing. It can be if the matrices have the right matching numbers in them, right? But this is the general rule here. They're not the same. To the whiteboards. Pause the video right here and take a look at these problems and see if you can work out the answers on the right based on the matrices on the left. All right, so C times D. Let's just take a look at the answer and make sure it matches what you got, and if not, let's stop and see what questions we have. So looking on the boards here, looks like you guys fixed yours in the back too. Does everybody's match up? Is there any part you're not sure about? Okay, sounds good. And again, if you're a little confused on this, you can go back earlier in the video to see how the multiplication works, but I think we're all pretty much there. So DC, I think everybody also got that correct. Looking around the room, it looks right. Yeah? Anybody have a question on that one? Okay. We might finish early today.
Party.
Party. Bring pizza, man. All right, that last one there. Looks like everybody got that as well. Yeah? Okay, good. And the final one is actually undefined, right? The reason it's undefined is because C is a 3x3 matrix and E is a 2x3 matrix. The inner numbers, in this case the 3 and the 2, would have to match each other, and they do not, right? So this one cannot be done. And the official term for that kind of matrix, or that kind of scenario, is undefined.
It's the question that drives us.
Questions? Just trying to keep you guys focused and laughing, that's good. All right, got to keep me focused too. So let's take a look at the identity matrix. That's the next basic idea here. And I promise there's a point to all this we're going to get to in a minute. And frankly, a lot of you were already familiar with this kind of stuff with the matrix. So my goal was to just sort of recap it. And then for the few who hadn't seen it, maybe just, clarify and make sure we understand it. So if you multiply the identity matrix with the matrix, it's the equivalent of multiplying something by 1, right? You have what's known as an identity matrix, and if you multiply that by some other matrix, the resulting matrix is the same matrix you started with, right? That's the basic idea here, okay? So what I'm trying to figure out is, if I have matrix B there, 1, 2, 3, 4, 5, 6, 7, 8, 9, and I multiply it by whatever A is with the question marks, what would A be to give me the 1, 2, 3, 4, 5, 6, 7, 8, 9 again? Okay, that's the basic idea. So take a look at what would I need to, if I want to get this first number here, 1, remember that's A11, right? So that means it's going to be multiplied by this and this, right? So thinking that from those terms, what would be the numbers that are going to go here in these 3 question marks? If you already saw it, you can spill it out. I'd prefer somebody who didn't see it try to figure it out, though. It's 1, 0, 0, right? Yeah. The reason it'd be 1, 0, 0 is because, remember, this is going to rotate, so that this right here is going to be multiplied by this. That's 1. And then if these are each 0, we're going to multiply them by this. That gives us 0, 0. So 1 plus 0 is equal to 1, right? All right. So, and we get 1, 0, 0. Let's take a look at, well, now will that work all the way through? Right? Because remember, row 1 multiplied by column 2 is supposed to give us this number, and row 1 multiplied by column 3 is supposed to give us that number. Does that hold? Yeah, that will work, no problem. Okay, so what do we want? What should the next set be right here? Remember, for this number, we're going to multiply it by this, and then for this number, we're going to multiply it by this, and for the last number, we're going to multiply it by that. So what would go there? 0, 1, 0, right? Everybody see that? 0, 1, 0, okay? Does everybody understand why that's the case? We good on that one? Okay. And if not, just do the actual multiplication. You'll see that that will pan out. The last one will be what? 0, 0, 1, okay? 0, 0, 1. So the matrix on the left there, we'll call it matrix A, whatever, that is the identity matrix. That's the equivalent of multiplying some matrix by 1, some 3 by 3 matrix by 1. If we had a 4 by 4 matrix, what would it look like?
1 to 1 diagonal.
Yeah, so you'll find the identity matrix is going to be 0 everywhere except for the diagonal, right? They'll all be 1s. This is the identity matrix. There's something else interesting about this that we'll talk about in just a moment. But what are some of the properties of the identity matrix? Thing number 1, I standing for identity matrix, right? I raised to the power of n will be equal to I, because you're just multiplying by 1 over and over again, right? I times b, not to be confused with IBS. Come on, that's hilarious. I times b will be equal to b because I is just the equivalent of 1. Dig it? And again, as I pointed out, you'll have everything will be zeros except for 1 from the diagonal left, from the left going diagonally, okay? If you want more details, page 180 talks about the identity matrix in your textbook.
It's the question that drives us.
Questions about the identity matrix? The next one, we mentioned possibly a transpose matrix a minute ago on the board. Let's talk about what that really is, and it can be very useful to us. We'll learn on the next time we meet. So the original matrix, if it's m by n, the transpose will be n by m. So in other words, row 1 from the first matrix becomes column 1 of the second matrix. Row 2 becomes column 2, and so forth, okay? Row n becomes column n, so on and so forth on down the line. So taking a look at this particular matrix here, 1, 2, 3, 4, 5, 6, this is what basically is going to happen. That becomes column 1, that becomes column 2. That's it. Row 1 becomes column 1, row 2 becomes column 2, okay? Pretty straightforward. This can be useful to us, I promise. We'll get to that, not today, but we will get to why that's useful. Today, I'm just sort of laying some pipe here, setting the groundwork up for the real reason we care about matrices. So the way we notate this is the matrix on the left, we're going to call it matrix A, then the matrix on the right, we call it A superscript T, the T standing for transpose, of course.
It's the question that drives us.
Any questions about that? So this is what it all comes down to, guys. Why do we care about these things? Those who have been exposed to matrices before, why did you care about them? What were they used for?
Linear algebra, you can solve equations.
Yep, linear algebra is huge. Any other uses? So using them to solve a system of equations, that's something you may have learned in your, probably, is that Algebra 2 that covers that, I think? Linear algebra determinants, it's another fun one. And if you don't know what that is, Google it. I think I have a resource coming up in a second.
The cross products of vectors easily determined.
Yeah, which is one I didn't even put on there, yeah, but good. So you said cross products of vectors. Also, computer graphics. Believe it or not, this is actually used in creating graphics on your screen. If you take, there's a really cool resource that talks about that for creating computer graphics. This website right here, Decoded Science website, that's a really, really good site. That's a really good site. It's got a lot of just cool information about this kind of stuff. We, however, discrete structure people, care about a very specific type of matrix. Anybody know what it is?
0, 1.
Yeah, 0-1 matrix, also known as a binary matrix, okay? We care about the 0-1 matrix. The reason we did all that other stuff we're not really gonna use in this class, other than today to make sure you have your head wrapped around how a matrix works. That stuff is probably more useful in your linear algebra or other types of classes. For us, though, we care about a 0-1 matrix. I just want to make sure we have a good foundation of how matrices work. So let's take a look at a 0-1 matrix. Obviously, it's a matrix that only has ones and zeros in it. It's very useful in representing relations. So let's take this relation here. Let R be the relation with the following ordered pairs: 1, 1, 1, 2, 2, 1, 2, 3, 3, 2. You can actually represent this in a matrix. This would be the matrix that represents that. Now, look, here's what we're saying here. This matrix represents which values exist, which values are true. So in other words, 1, 1 is true. Well, remember, this is A, 1, 1, right? Row 1, column 1. So you can treat the A and the B, this A as row, and this is the C, the column. 1, 2, that's row 1, column 2, right there. We're saying that's true. There is no row 1, column 3. There's no 1, 3 pair, so this is a 0. And then we have 2, 1, right? Row 2, column 1. There is no 2, 2. And then row 2, column 3 is right there, this guy. And then the last one is row 3, column 2. That's this guy right here. So this matrix represents a relation. If we're using this particular representation, we can have a 0-1 matrix that represents our relation. Why is this useful? Which we'll learn about in a few days. It helps us determine properties of a relation. What property does this particular relation have? Don't look at the matrix, just look at the pairs. Symmetric, okay. Anything else? These are the 4 properties in the rules, just as a reminder. So far we got symmetric, that's correct, it is symmetric. So you are correct, that is it. How do we know that it's not reflexive?
When you 2, 2, and the 3, 3.
It's a good question. Why 2, 2, why 3, 3? So why, you're right, there'd need to be a 2, 2 and a 3, 3. Would there need to be a 4, 4 and a 5, 5? Why not?
Index out of bounds exception.
Nice. Index out of bounds exception.
The ring looks like it's only going up to 3.
Right, and remember a relation, when we look at these properties, we're talking about relations on themselves, right? So the original relation only had 3 things in it. And we did a relation on itself, which would give us our ordered pairs. How do we know it only had 3 things? Well, because our matrix is 3 by 3. Whenever we're dealing with relations that are relations on themselves, then the matrix will always be a square matrix, because no matter how many elements are in my first set, there's 100 elements in it. If I do a relation on itself, then you have 100 elements being related to 100 elements, right? So it's still square. So in this particular case, you cannot tell, or you can tell that it's not reflexive because we don't have a 2, 2, and a 2, 3. So you're barking up the right tree there for sure, Jace. Antisymmetric. If AB is in the relation and BA is in the relation, then A must equal B. Well, again, just looking at the ordered pairs there, we have a 1, 2, and we also have a 2, 1. And A and B are not equal in that scenario, right? So that is invalid. If you have one case, it's invalid. Transitive, that means if you have an AB and a BC, then there better be an AC. And if you go and follow that through, you'll find that it will not be transitive. I think one example would be, we have a,
1, 2, 2, 3, you don't have a 1, 3.
yeah, so we got a 1, 2 here. And that means, so that's our A is the 1 and our B is the 2. Now we're looking for something that starts with B, right? And here's something that starts with B. And then there's the C. So that means there needs to be a 1, 3. And there is not. So it's not transitive. Now, why is this useful to us? Well, if you look at this matrix here, and we sort of block out the center, this is one way to use a matrix to tell what properties it has, what properties the relation has. If we block out the center diagonal right there for just a moment, and then we look here at the ones or zeros on either side of the diagonal there, you'll see that both ordered pairs are there. In other words, this is 1, 2, this is 2, 1. That is the definition of symmetry. If there's an AB, then there's a BC. See that? This is 3, 2, that is 2, 3. And we have, there's the 2, 3, there's the 3, 2, there's the 1, 2, and the 2, 1. So by looking at this picture, you can very quickly tell that it's symmetric. We're going to learn way more about how that works and how to look at the images of a matrix and see what are the properties it has. This is just to kind of introduce you to the basic idea. Before we fully learn about how to use these in relations, we need to make sure that we understand a few more things that are going to be on the next couple of slides. So taking a look at this matrix here, this is the one that we just looked at on the previous slide that's symmetric. One other property that's true about a symmetric matrix is that the first matrix will equal the transpose of that same matrix. So let's just remind ourselves, what does it mean to be the transpose of the original matrix? Remember, row 1 becomes column 1, row 2 becomes column 2, row 3 becomes column 3. If you look at that, I just rotated the numbers so they're upright, but that is the exact same matrix. So in that case, it is symmetric. Whenever that happens, it will be symmetric. Chapter 9.3, which is the topic of our next lecture, next time we meet, covers this in depth.
It's the question that drives us.
So questions about just this one little example of how a matrix can be useful to us. The whole first half of the day today was all about just a matrix in general, how they work, how you do math on them. It was to prepare us for going into binary matrices or 0-1 matrices and how to use them in our world of discrete math.